CEO construction and was involved in major projects like the Blouberg Netcare Hospital, the one and only hotel in the V&A, Waterfront, and Greenpoint Stadium. He joined SMEC South Africa early in 2009
to check the vacancy.
and worked on some more prestigious projects, such as bridge projects across South Africa, including the award-winning Mount Edgecombe interchange. Currently, Gerrit is on the N2 Wild Coast Bridges, where he's currently the technical resident engineer on the Msikaba River Bridge project. And Gerrit holds a BTech degree in civil engineering structures and is professionally registered with EXA. Join me in welcoming him to share with us this interesting presentation.
Thanks, Gavin. I'm not sure if everybody online can actually see the presentation.
There's just one screen in front of the presentation, or you need to open that presentation. Sorry.
Oh, the IT specialist has turned up again. It wouldn't have been right if there's been swimmingly at the last ones. Yeah, so I think I can start in the meantime for what it's worth. So yeah, thanks, Kevin, for the introduction, Mohammed, and for the opportunity to be here today and to discuss a few technical issues, I think, with everybody.
Thanks, 100%.
Is it on? Yep. So yeah, like Elsie said, I don't know if it's a blessing or a curse to do the graveyard shift, the very last presentation in 2 days. So I can see there's some conference fatigue out there in the audience at the moment. So I'm going to try and keep it interesting at least. So yes, the presentation is about grouting, inclined post-tensioning tendons, and that's sort of the technical part of it. But I also thought it's a great opportunity to just share the Msikaba Bridge project in its sort of entirety in a very brief few slides. It is probably one of the biggest projects ever done in South Africa, definitely currently underway. I know there's a lot of big ones starting and a lot of people here involved in those. But for the moment, it's still the biggest and still one to be proud of. So let's get into it. So just in terms of the content, we're going to be looking at the bridge, like I said, and then we'll move on to the more sort of, say, technical bit, which is the grouting of the post-tension tendons. We'll just look at some of the requirements, the grout trials, as well as the outcomes. So this is just a picture of the bridge. This is taken a few months ago, but it does give such a nice perspective of the gorge that we're actually trying to span. So just some contract information. If you don't know, the bridge was designed by SMEC South Africa in a joint venture partnership with a company called Jacobs, or formerly Alcra and Axis. And we formed the HVA joint venture. Also, the design was originally done in 2002. And I don't see Ravi here today. He was here yesterday. I actually thought yesterday he's about the only one that was really involved in the design. I don't know, Roger, were you involved? So 2 people that was actually involved in 2002, and Edwin. Yeah, but Edwin, we know that. So obviously, our original design done in 2002, then shelved for a few years. Pulled off the shelf in 2016. We did a design update and then went into implementation in 2019. So the supervision is also done by SMEC South Africa. The contractor, as some of you might know, is a joint venture called CME, which is Concor, a local entity, and then Motor Angel, which is a foreign entity. The employer being Sunrail. And then at this stage, we're looking at about 2 to 2.1 billion rand for the final completion cost. And just some facts and figures about the bridge. And again, this is just a very, very short overview just to give you guys some information about the bridge. So it's got a deck span of 580 meters. It is a stake cable bridge, if that wasn't clear. So, sorry, at this stage. The height above the valley floor of the deck is 192 meters. Earthworks about 800,000 cubic meters, of which about 500,000 cubic meters is in rock. Concrete about 50,000 cubic meters. The rest is not that impressive, to be honest, but the stake cable figure is end to end. So we used multi-parallel strand stake cable. So these are the normal 7-wire strands that you all should know or is aware of, same as PT. And So about 1,100 tons of PT strand will be used to, or not PT strand, stay cable strand will be used to form the stay cables, and end to end, that's about 930 kilometers worth of strand. So then there's a video clip. You would have seen this clip, and it's just a coincidence. It's the one. I don't know if the guys at the stall actually stole this for my presentation. I don't know, but it's the same video clip that's playing outside at our stall. So this is just a fly around to show sort of progress at the moment. What you can see in the background, there was the two anchor structures, which we'll touch on just now. We'll see the pylon structure now, which is in an inverted Y shape. So these are 127 meters tall. The deck, like I said, 580 meters, 192 meters above the valley floor, which makes that the second highest bridge currently in South Africa. Will become the third highest after M10 once that is completed. Yeah, and as you can see from this pylon, this is the southern pylon. That's at about 45 meters height in this video. So which basically roughly transferred that the yellow tower crane that you see there, that's about half the final. Well, the tower crane is at exactly half its final height. So double the crane height is the pylon heights when it's completed. Okay, so just a quick look at the pylon structures themselves. So like I said, they're these inverted Y-shaped piers or pylons, and the legs actually straddle the roadway and you drive underneath the legs. 127 meters high, so circular shape. And from the top of the bifurcation, which is just where the legs actually come together, it's got a radius of 6 meters and right at the top 4.5 meters. So what you can see, if I can just find it's IT. It's IT when you need it. Sorry, just bear with me. Here you go. Yeah, so this is just a 3D model, if you like, of the style of the pylon liner or anchorage. So in our bridge, the stay cables obviously anchor in the pylon, and they are actually anchored there. They don't pass over. So those are dead anchorages. And so they are anchored into these steel pylon liners. That's what they look like. These are actually being manufactured locally in South Africa, up in Johannesburg. And this is sort of just one of them in progress. They range in weight from about the lightest one is about 6 tons up to about 11 tons. So the deck is a steel concrete composite deck. As you can see in the picture here, this is the steel part, and that consists of these two longitudinal box girders, and they connected with these truss type cross frames that give them stability. The deck is made up of 17 typical deck segments per side. So obviously we're building the deck from both sides, from the north and the southern bank, in segmental construction. So the deck segment's typically 15 meters long. What you see there is a typical segment. Just to give it some scale, I like this photo because it actually puts it into perspective a little bit. So 17 each side, and then in the center, there's a central joint, and that's made up of two segments, say 18 left and right, we call them, and they house the actual joint, expansion joint details. And then obviously it's got a 250 millimeter reinforced concrete slab on top. So then moving to the anchors at the back. So I put this slide sort of at the, we're going to talk about these just now because that's actually where the grouting happens. So we got to circle back to these. But in short, we've got something called a gravity anchor, which sort of does what it says on the label. The anchors are not positively or mechanically connected to the rock mass at the back. They are just literally heavy enough, big enough that gravity itself does the work for us. So it keeps the main span and the mainstay cables up. So as you can see, 49 meters by 10 meters by 17 meters deep, which is a substantial excavation. And you can see there's a few that actually also is. Yeah, so you'll see some guys in the bottom of the excavation here, and keeping in mind that excavation wasn't complete yet. And this was all done with highly controlled blasting excavation. So in an attempt not to fracture the surrounding rock. So question that I usually get. So this is a 3D model of the anchor block, and people immediately look at it and they go, why the shape? You know, why the funny step shape? And so that's really for the structure to interact better with the surrounding rock mass. So even though it is a gravity anchor, so it is heavy enough, it is also trying to be dragged forward by the cables. So that gives it better lateral stability, as well as helps with the overturning of the base. Okay, so this is just a short animation, and I've put in a short one just to show you the deck erection sequence, because I think it's very interesting and it sort of just ties everything together without having to talk for an hour. So obviously every deck installation starts with the installation of the backspan cable. This is obviously quite important to stabilize the pylon before you do anything towards the gorge side. So what you see here is what we call the launching gantry. So this weighs, I think that, David, I don't know where you are, what's about 180 tons now, the final version, 160 tons. So this obviously takes the deck segment, which is rotated at 90 degrees, so that it can fit in between the launch gantry legs. The segment is then lowered into place. We make use of an underslung gantry. So these are left while refurbished and then left in place. There's two, one for the south deck and one for the north deck that will be used for maintenance in future. But during construction, they're used to actually do the welding up of the box sections. So once the welding is done, the mainstay cables are actually installed, as you can see going up there. At this point, the gantry actually, so the sequence has changed from this video. So once the welding is done, the gantry can actually release the deck segment as it can sit under its own weight once welded. So I've actually stopped the video here, I believe, but so after this, we'll use the same underdeck gantry to actually install, I want to say, conventional formwork, soffit formwork in between the frames, then do reinforcing and in situ concreting. And then obviously the cycle repeats itself. Okay, so that was the bit about the bridge. Hopefully that's kept you awake for now at least. So I'll see. I'm going to try to not put you asleep now. Okay, so I said earlier I'm actually supposed to talk to you about grouting, technical cement or concrete related topics. So this is my topic. So we have something very unique about the anchor blocks are these post-tension tendons, so which I've highlighted in red here. So as you can see, they go down to the full depth of the anchor block, do a complete 180 and come back up. So, and they follow, there's a set of PT or a PT tendon for every backstay cable. And so the idea of these are actually to activate, say, literally activate the full depth of that anchor block. So we're very dependent on that weight of the anchor block being a gravity type structure. So that's what that PT strand actually does. It sort of activates and transfers that load all the way to the bottom of that anchor block. But what this does present us with is, so what's quite important to note as well, the backfilling that you're seeing here, this is actually all mass concrete as well. So what the problem that this causes us in terms of post-tensioning, and many of you would have been involved with post-tensioning before, but this puts the post-tensioning completely out of reach forever. Once it's cast, it's cast. There's no going back, there's no reaching it, there's no fixing it, there's no maintaining it. So for that reason, and being a bonded system, the grouting is significantly important. There's no chance of getting it wrong. There's no chance, and there's no way of going back and seeing whether it is right, in fact. So that was a problem we faced. So how are we doing for time? That's still all right. Okay. So just in terms of I want to say conventional post-tensioning, this is what we know about. Anton spoke about earlier in his bridges. This is what we know. We know drape tendons. Amongst us all here, it's mostly in bridges, and in some building slabs, you get some bonded systems. But basically, this is what we know. And you see the H that I've identified there. So that differential height, if you like, between the highest and the lowest point of any tendon in civil structures aren't that big. So they're actually negligible in terms of hydrostatic pressure differences. So which means there's very little bleed water. And so bleed water is quite significant and quite an issue when it comes to grouts. But like I said, we really deal with it because of our low profiles and our small height differences. You'll all be sort of used to dealing with it in the vent pipe, extending the vent pipe up the top and then closing them off, and you'll have the bleed water settle in that pipe and you cut it off and it's not a problem. So we see that the standards that we specify in terms of EN 445 and 447, that those standards actually deal very well with that, which I sort of consider conventional post-tensioning and conventional grouting in terms of how the material acts, what those flow times and those water cement ratios are, and those testing methodologies. Apologies. So, but what we found soon found out is that that's not the case necessarily for the Mississauga tendons, because of the 41-degree incline and especially the 16.5 meter height difference. So that significant elevational change, that does cause a massive hydrostatic pressure difference. And so what this means is while the grout is uncured, it bleeds, and it bleeds a lot. And so this was one of our biggest problems. And so we soon found out that some of the, not all of them, but some of the standards, or say the requirements of the standards, don't necessarily fit that well into this picture as soon as we start talking about these sort of hydrostatic pressures. And the biggest one actually being flow time. So most people will know, if you've dealt with grouts, we talk about flow times in seconds, and these standards say shorter than 25 or less than 25 seconds in a standard flow cone. So we found out that that doesn't actually work so well, and I'll discuss that a little bit more just now. So challenges, I just mentioned it. It's bleed water basically, and that was one of the main questions. Was could we actually control the bleed water, or would we just end up trying to manage that bleed water? That ties into water cement ratios. So because unlike concrete, this is without aggregates. So water cement ratio completely flat out dictates workability and flow times. We weren't sure what the pressure gradient was going to do. Obviously, because of that steep incline and that quick displacement of the bleed water, there's no time for reabsorption, which is one thing that we also bank on a lot when we're grouting, is some reabsorption of the bleed water. Then obviously there were some considerations in terms of workability versus setting time. So similarly, like I said earlier, very important that it's still got very good fill ability, to fill up the tendons properly, but setting time just as critical. Because as I said, completely inaccessible. So we had to make sure that there's sufficient time that should something go wrong during the grouting process, that there's enough time to actually flush out the ducts completely and evacuate everything. Because if we couldn't, or if we can't, I say couldn't if we can't, because we're yet to grout actually. If we can't, then we obviously end up with a massive problem, because there's no way of going 17 meters down into solid concrete to try and find a blockage or undo a blockage. And then obviously repeatability and robustness. We've got 17 sets of cables. I mean, that's 68 of these, and we can have a 0% failure rate. There is no room for error. It has to be 100% correct. So obviously it needs to be a robust process, which deals also with the remote nature of the site, the labor that we have, the technology that we have out there, and we need to be able to repeat that very successfully. And then obviously less of an issue compressive strength, which we all know is 20 MPa in 7 days. So that's actually least of our problems. So all of this, there were some we had a wise client, Edwin, again, thank you, a wise employer and wise engineers at the time, who actually realized the significance of this grouting operation and the fact that this was different to the norm, and therefore was actually included in the bill of quantities as a pay item, and then specified in the specifications as well, with some requirements for full-scale grout trials. So then just in simple terms, so what was the purpose? What were we trying to achieve with this? It was obviously to ensure, number one, high quality product that's durable. Like I said, no access in future to actually work or maintain or fix anything. And then the idea was to simulate the worst case scenario of all the tendons. So this is the longest one with the steepest incline with the most angular change. And then obviously to test the methodology, which includes the equipment, even the personnel. I think we like literally the people that's going to do it. And so on your right-hand side is a picture of what it looked like. Then just some details with regards to it. So the contractor actually built this ski slope. We call it the ski slope from a earthfall. And then at the bottom, there's a concrete, sort of call it anchor block, if you like, which houses the steel circular section of the tendon. And then at the top, there's some slabs, which actually on to which we put the anchorages and from which we seize the tendon off. And then the grout mix is obviously pumped from the top. So if you can imagine, that's the top of the anchor block there. And then the injection point is actually at the bottom of the tendon. And so we used 7-strand anchors that we fully occupied, so 7 strands, and you stretch them up to about 10 tons. And this is sort of a neither here nor there figure. It was just actually to ensure that the strands were seated and that the profiles were straight. And then obviously, yeah, we did our trials, we geared them, we cut them up, and we actually assessed the results. And so we actually went with a smooth duct as opposed to a corrugated duct, which is what is specified in the permanent works. And mainly the reason being the smooth duct is actually the worst case scenario. So with the corrugations, as the grout travels up, there'll be some mixing of the bleed water as it goes up. With a smooth duct, that's not the case. So we're getting the worst case displacement of the bleed water. So if we could deal with it in that situation, then we'll deal with it in a corrugated sheet much easier. The corrugations also catches some of the bleed water, which leads to reabsorption. Okay, so this bleeding phenomena that I keep talking about, and again, that question about can you control it or can we just manage it? And we figured there's only 2 ways, and that is through material performance, which is the actual grout product, how we mix that, where we get that from, what that material sort of looks like, and then there's the methodology, how you actually do that. Or it could be a combination of both, which is what it turned out to be. So just in terms of the material, yeah, we're obviously looking at water cement ratio, but also actual, I want to say, grout product. The interesting thing here is that we started off this exercise by importing very expensive grout, first from America and then from another country. And at the end, we ended up using a locally developed grout from South Africa, which actually performed the best. So, which was quite interesting. And with the methodologies, it was actually the same thing. Our very first trial was done from a method statement received from overseas from the so-called experts in the world, and it didn't work. And we actually ended up developing the methodology, I want to say ourselves here locally. So interesting thing just about the material is because water cement ratio dictates that flow rate, and it dictates, in other words, that workability and that bleed water, that dreaded bleed water. What we found, obviously, and it is quite obvious at the end, but because of the way we set up the grout trial, it sort of it does become lost on you a little bit when you look at the pictures. And I'm just going to go back to that picture. So in the real application, obviously, we are at ground level, and this is all happening below our feet. Where we've done our trial, this is at an elevated position. But one forgets that you're actually grouting, your grouting equipment is sitting right at the top, and you're grouting at the bottom. So you actually don't need a lot of pressure to fill up those. You're thinking that you're grouting against 17 meters of head, but you're not. The grout just wants to even out from the grouting tank at the top. So what that actually meant is, without having to actually exert all that pressure to try and get the concrete or the grout 17 meters up, because you don't, it means that the workability didn't have to be that good. because we didn't have to push it that far like you tend to do. So this actually gave us an opportunity to considerably reduce the water cement ratio. In other words, take a lot of the free water out of that mix, and through that actually reduce the bleed water significantly. So as you can see here, here's some of the tests we just did on the grout. We were marking the bleed water and the grout levels as a sort of in time, just to see what the different products were doing. So I'm going to just try and move on a little bit. So here's some of the results. As you can see, there's what we call bleed affected grout. So this is where the bleed water still sits within the grout. So it's not the water on top. It's a portion of grout just below that, where the water is still very much sort of mixed into that grout. So we're almost at the end. This is just the 3 trials that we did, so don't worry, we're almost there. So the first trial that we did, like I said, so this was an imported, very fancy. I mean, even some of the equipment was imported. I'm not going to say by who. But as you can see, there's a very fancy vacuum pump there. It's the first time I saw any, I've ever seen one of those. And so this methodology in broad strokes sort of consisted of, again, a fully occupied 7-strand anchor with strands. It has a re-injection valve, if you like, or call it a vent. We call it a vent, but a re-injection valve just below the anchor. You actually can't see it on this picture. So in broad strokes, and I've got a nice slide after this that will show it, is you basically inject the grout up to the re-injection valve. Then you apply your vacuum pump for an hour. And so this vacuum pump is supposed to then actually assist in drawing up the free water and the bleed water to the top. After the vacuum pump, you actually wash out or blow out that bleed water. You let it cure. You clean it again the next day, and then you grout up the remainder. So in short, this is sort of what it looks like. So yeah, this is the vent pipe here. So this is just a schematic to make it easier to understand. That's sort of a grout cap, that's the anchor, and that's the duct. So first step was injecting the grout up to that point. Then there was we call it an evacuation, process where you actually blow out some of the immediate bleed water. And then 24 hours of curing, and that is sort of the effect. We then blew that out, and what we figured out is that only took out the actual free water and not the grout affected or the bleed affected grout. So after re-injection, that's what we ended up with. So that bleed affected grout portion that you actually see there very, very nicely. So that was just completely brittle. It had no integrity whatsoever. I mean, it was completely useless. So obviously, we saw that this wasn't going to work. And at that point, questioned the vacuum pump as well and its purposes. So after this, yeah, so these are just some more pictures of what that zone actually looks like, that bleed affected zone. So then we had another crack at it. This time again, 7 anchors. But so what we obviously learned at this point is that rather than trying to get the muck out from below the anchor, we'll just grout past the anchor, into a reservoir at the top, and then let all the bleeding and settling happen up there and it's outside. So very similar to what we do here in South Africa with our standard PT and vent pipe. But there was a catch. You'll see now why. So this is a simple, the logic is there. It was the execution that was, we needed one small adjustment, which you'll see. So we injected that, we left it, and what we found is that some of the bleed water does in fact migrate through the anchor, but the bleed affected grout does not at all. So that remains and got stuck below the anchorage. And so as soon as we cured it and we stripped the anchor off, we found that there was no grout inside the anchor and in what we call the trumpet bit, the anchorage behind it. And so this was very clearly because there wasn't a clear path path of for the bleed water and the bleed affected ground to actually migrate. So this we solved in our final. So this is just some pictures again. You can see the bleed path very clearly there. And this is in the reservoir. So you can see there was a little bit of, call it rubbish at the top, but not nearly enough in terms of what collect. And so this is the modified version, if you like, of method number 2. So you'll see it still has the reservoir at the top because this is a good idea. It was always a good idea. But this time we've actually created a path through the ground cap itself. So we've closed the ground cap up. We have a bleed screw in your normal ground cap, so that we've closed up, and then allowed, you know, the bleed water and bleed affected ground to actually travel through the ground cap and into the reservoir. But apart from that, we also left it for 2 hours after the initial ground. So allowed the initial ground column to bleed, and then re-injected fresh ground for that last portion. So, and actually this worked very well. So again, just in terms of how that looked, so that was the initial ground injection. We waited 2 hours, and that's sort of basically what's happened. So you can see the main difference being that there's a path there for most of the rubbish to move past the anchor itself. And then obviously after about 2 hours, we just re-injected. We actually did another trial. After 2 hours, we actually washed out. So instead of re-injecting, we actually forced water with air pressure in here, and we washed out this whole system, and then came back the next day and re-grouted it. And that actually worked as well. But this is obviously less steps, so less prone to errors. So this is the system that we actually went with. So as you can see, so this is in this connection, which is, I mean, 100% perfect ground. So these are just some of the samples that we took. And again, so that is a bit black just from the grinder blade, but you'll see that that's perfectly filled, even in between the strands or the wires, and absolutely no problem. So what did we learn? We learned, in fact, that bleed water can only be managed. You cannot control it under these circumstances completely, and you can only manage that by material selection and material control, as well as methodology. We now understand that migration part is probably the most important thing, is at those pressure differentials, getting the bleed water from the bottom of the tendon to the top of the tendon is not a problem, but getting it past your strands and past your anchorages, this is where it's quite vital. We've spoken about the re-injection, the workability, you know, that's not affected by the lower water cement ratio, which is quite a weird. So again, the standard wants us to have a flow time of less than 25 seconds, right? So which is very, very fluid. We are grouting very successfully with a flow time of 55 seconds, to put that into perspective. So which is double what the standard actually requires. And we have no problems. We have setting times which are very long, or long enough, let's put it that way. We've got perfect filling ability, and we've got very little bleed water to deal with. Yeah, and then the very last point, I think, which is such a nice point. We always, you know, when it comes to things that we don't know, especially in the engineering fraternity, we tend to sometimes run overseas. No offense to all our overseas guests, but we sometimes run overseas. We think, you know, we're going to find the answer abroad. And 9 times out of 10, you know what, we actually have the ability to find the answers here. So it's a true testament of sort of our abilities as civil engineers in South Africa. And that's my story. So thank you very much for listening.
I didn't even ask for questions, and I see some hands already. Thank you very much for taking us all the way to the end of what I'd say is been an awesome 2 days so far. And I think highlighting the finer details on such a prestigious project just opens up, I'm sure, a couple of questions and insights as well. And it's a lovely note on which to end this conference as well. Bringing together all the engineering, but then also focusing on the details of the materials that makes the engineering possible. And so with that, once again, thank you very much, Herr. Are there any questions?
Two minor questions from my side. First one is, how are we doing in terms of steel supply? I remember when we were doing the HCOM and we came to see you, there were some issues there. It's even more complex task. So how are we doing? The second part is, I don't remember when this tender went out. Is this a full new quota standards? So in terms of quality, your monitoring which you are doing, it does put more emphasis on contractor side to have its design and experienced experts to make your life a little bit easier, or you have to run every single details, check compliance with every single test and make sure that you certify. How is it working today?
Yeah, thanks, Tiago. So to start with the reinforcing, I'm assuming you're talking about reinforcing steel. So yes, we vividly remember the issue at Mount Edgecombe. But no, so yeah, definitely much stricter control, and I think on the back of lessons learned back then. So much stricter control in terms of material delivered to site, mill certificates being checked by ourselves and by the contractors. We in fact actually went prior to any steels, reinforcing steel being delivered to site, we actually went to the suppliers and where they're bending the steel, and we actually went and inspected their facilities. And this is for the reinforcing. So yeah, we haven't had any issues so far. All's good, all's well. Then in terms of the specifications, so these projects, they were done still according to Colton. So you sort of correctly, you've mentioned the contractor's design items, and sort of they do have a real big responsibility in a project like this because of the really, I want to say, big amount of erection engineering that goes with the construction of a bridge like this. But I'll be very honest with you, Tiago, I don't think our specification, even though it is still under Colton, I don't think by any means falls short of anything that Koto is today. I mean, we still have Edwin as well involved in the project, I will not say on a daily basis. We consult with the Koto document very regularly in any case, so we're always double checking to see that whatever we are doing on the structure is still valid and it sort of holds with the new Koto document in any case. But yeah, the specification is, I want to say, quite amended from the original Colto document in any case because of the technical nature of the structure. So at this point, I don't think that we are sacrificing, I want to say, any quality or any technical quality, at least on the structure, not by a long shot, to be honest. I hope that answers your question. I know.
Thanks. There aren't any further questions in the audience. Online, is there anything, Basil?
Sure. I'm going to ask the quick one first. Rod Rankin says, thank you, Gert. Very interesting. Are you at liberty to name the local brand of grout that you found to work best?
Yeah, I'm not going to do that.
Okay, all right. Then
that's okay. But you can come and visit the site and then snoop around under supervision.
There's some of the Muti line there somewhere. Okay, just a joke. Then just a question, any specific reason why the tendons were not installed and fully embedded directly into the in-situ rock mass rather than using the gravity anchor block?
Yeah, so overseas, and I want to say in Europe, they don't actually have many, or I say not in Europe. In Europe, they do actually have problems with mechanical, say, connections, so-called rock anchors. And so, and because we have a European or an English design partner as well, they weren't in favor of this in the beginning. And I have to admit, at the end of the day, this is, for me, I prefer this. This is safer. There's no, there's nothing that can sever. There's no life span, if you like, or durability issue with a connection, I want to say, or the ability for the anchor block to actually counter the forces exerted on it. Anchorages can rust, they can move in time, there can be slippages. With this solution, I think is the safer one, at least. But yeah, in the rest of the world, they're not too scared to do that. We here in South Africa, we also do it. This is unique. There's nothing like this in South Africa. So I think the safer, more conservative route here is the better one, if you ask me. So.
Great, thank you very much, Gert. Thank you very much to our audience online who've asked questions as well. That brings us to the end of the structured sessions, and I'll hand over to Krishna, who will be closing for us.
Thank you. Thanks for staying the course. I think we still have like 5,000 people who are still online with us, and there's like another 200 in the room, and there's another 300 outside. So yeah, it's been an epic 2 days, and last night was epica, right? Thanks for the red, white, and some of the blue as well. Did anybody have any blue last night? Nobody. Yeah, it's been quite good. Certainly from Sandra's perspective, we are really grateful that we've had such a response. Hanli, I think we've had probably a better part of 800 plus odd people that were registered. Our IT guy is still trying to confuse us. And Hanli. Reverse bezel would be 2 minutes. And there was deadly silence. Anybody knows any concrete jokes at present? Any rebar jokes?
One of our resolutions.
One of the resolutions is that we need to come up with bad concrete jokes. But they still need to be durable, right? Thank you. So yeah, as I said, from Sandra's perspective, CCS, SA, CSIR, SAF, we're really grateful for the response that we received. 800 odd people that were registered. On any given day, we were probably looking at a better part of 400 or 500 at peak. We were what, probably 500, 550. When we started off, I said that the organizers were these four bodies, but as it turns out, I've been taught a lesson. We have 27 presenters. They stepped up, gave their time voluntarily, their knowledge and understanding voluntarily to all 800 of us. They were far better organizers than we were. We had this wacky, weird, wonderful idea and ambition, but they pitched up, turned up, and delivered very, very high quality. So a round of applause to all of the presenters. So that was our team at the beginning, but this is our team now. 27 presenters, 800 odd registered attendees. The peak, more than 500. I know somebody was saying 550 odd or something like that. 100 odd to about 150 we had at the venue, in and out kind of thing. 3 suppliers, I stand to be corrected on that. 10 project teams, that's from the N2, N3 corridor. There were more people there as well. 2 keynote addresses. 2 keynote addresses, a keynote address every day. They're definitely part of our team. The why bit, I started off by saying that this is why we're having it, and I think these objectives have been met. If I'm misplaced in my judgment about this, please by all means raise your hand, and we can go and have a drink and talk about it. The platform bit, now there is the platform established. We need to move it forward further and on to bigger things as well. Volume of concrete that has been discussed. Imsigaba has been discussed. A couple of other things have been discussed outside. The guys were talking about all of the projects that we're going to go through and are going through. So there's definitely quite a bit of volume. Generate more knowledge, expertise, and capacity. Guys, this is international level from, well, it is definitely international level, but the amount, 2 days with each person taking us really to the edge in terms of how much time we allocated to them. It's really wonderful to be part of this process. Technology transfer, there's quite a bit. We heard from Peter Taylor. I'm super excited that the possibility that we may be able to engage him further. Generate new research needs, a very big yes. Benoit, who's from CSIR, he's been taking notes furiously. Value proposition, all greens. And some sponsorships came through for Gift of the Givers. We are really grateful to the guys. It's still open, Hunley. Guys, sponsor, please, by all means, go to the website. You've heard the doctor early on in the day. I think we can all do with the helping his organization a little bit further. This was a failure, road maintenance. I tried to steer it and stir things up. I didn't get any responses. It's a big gap for us in our industry as well, and Brian has recognized this as well. We're building all of these wonderful roads, but we will have to maintain this. So next iteration, we will be giving this a little bit more attention and focus. Flagship personnel projects, we did really well. Info there was streaming live from all of the project teams and the exhibitions. I thought that came through quite nicely. So we started off with this unfulfilled, not completely fulfilled. So hopefully we continuously reinforcing industry strengths, crystallizing cement, bridging the gap, cementing relationships, Hanley. And Thiago, you're seeing light at the end of the tunnel someday and overcoming barriers. So with that, I'm going to hand over to Brian to take us through the draft resolutions that we've come up with as organizers. Thank you, Brian.
Thanks, Krishna. These were put together by Benoit. So if I can just go through them. On day one, further research be undertaken on emerging supplementary cementitious materials such as calcine clay, also to support energy saving and reduce CO2. There's a lot of that research already happening at some of the universities. The cement industry is pursuing the net zero by 2050, so that's happening. The Koto standard specifications be updated to account for new cement types while allowing for review of current specifications set for concrete use. I think Peter Taylor talked about some of the test methods that we maybe need to relook at to make it specifically for concrete pavements. That research be undertaken to render our transport infrastructure more climate resilient. Also on day one, with respect to target reliability criteria set for serviceability of road-related structures, the TMH7 be upgraded, focusing on target and service reliability. That active crack control be further investigated for implementation on CRCP, and I've spoken to Krishna that maybe we can do some trial sections on some of the current CRC that are happening. Use of alternative, recycled and or artificial aggregate, as well as RCA crushed sand, be further investigated for application in concrete pavements in South Africa. Also supporting the development of protocols and specifications informed by experiences overseas. Also that the use of RCA in other applications such as backfills, unbound aggregate shoulders, cement stabilized lean concrete subbases and asphalt also be further explored. As you can see, Benoit was taking extensive notes. That non-technical barriers, those resulting from lack of information, preventing the use of RCA be overcome by provision of better access to information, as well as technology transfer activities. That quality management plans be revised and improved on, and that additional tests such as the resistivity test be considered for inclusion in the quality control plan. That vibration technologies and techniques require urgent attention. Peter Taylor mentioned over vibration may cause too many fines to raise to the surface of the concrete. On day two, the development of a TRH guideline on tunnel design and construction be considered. That the pull-out test for assessing bond strength be further investigated to improve accuracy of the method, and or that an alternative test be investigated. That improved guidance be provided regarding moisture conditioning of the substrate surface prior to the application of a concrete overlay. E.g. in the USA, no wetting is done has been found to adversely affect performance. That all road restraint systems, barriers should conform with the requirements of an appropriate standard. that hazards associated with untreated barrier ends be mitigated. I'm not sure if there are any more that we need to add. I think if there are, you can just drop an email to Krishna or myself, and we can include them in the list to talk about future research. Other than that, I think just thank you for joining us from CCSA and the other sponsors. And I'd just like Hanley to give you details of the CPD presentation, where you get your CPD points. So from me and CCSA, thank you very much.
Thank you. And shortly, we're going to put up one slide just to explain to you how you can get your CPD points. Just to tell you in the meantime, no physical CPD certificates will be issued. It's all online. It will be there. And we're going to get the slide up any moment now. There you go, in presentation mode. So Natasha will send out, Natasha's the lady with whom you've registered to attend the seminar. Natasha will send an email to all those people who've signed the attendance registers or who were downloaded from the Teams, the online attendance, as soon as all the detail have been uploaded onto the website. All the information to actually access that certificate will be on the website. And as I've mentioned, no physical certificates will be issued, but the CPD number works as follows. What you see in turquoise there is the number of this event, the CPD number, and then the number in the black will be your personal attendance reference, which you will find on the list, provided you attended this, provided you've signed the attendance register if you were here in person, and provided the Teams records show that you were attending on the days. So, but Natasha will send the email as soon as everything has been uploaded onto the website. Thank you.
Thanks to Hanley and Krusha there at the back. They've been the backbone, and Basil and Jabu, they've been the backbone of keeping the admin together. We really appreciate that. The fellow focus area chairs, and the likes of Zain and Dumi, really thanks for your guidance, your encouragement and energy. I should stand here, right? So, we need to tag. So we need to tag. Thanks all IT guys. Well done. And thanks to the venue, the organizers, and the food. It was really great. We had really great feedback from everybody. Much appreciated. Do drive back safely wherever you're traveling to. I've had loads of questions already about the next one. Watch this space and watch this brand. You definitely will see a lot more action from this perspective on this particular brand as well. I appreciate your time. Thank you very much all.
And thank you to Krishna. It was your driving force that got us all to do this, Krish. Thanks. Well done.
Most welcome, Basil. Most welcome, Basil. Thank you.
Cheers, everyone.
Invites, eh?
Take care.
Thanks so much.
Cool. Thank you.
If you see the thank yous online, there's plenty coming through, Krish.
Thanks, Basil.
Obviously good news. Sorry, man. Just finishing off.
Put the aircon on.
No, it's finished. We finished 2 days of craziness. in my
Get the
life.
stuff from underneath. Thanks, Basil.
Let me shoot off this.
Yeah, we still have 40 people.
For the project.
Oh, that's good.
I'm also saying. Anywhere in the country, you know, we move. If you can pay for the accommodation or Krishna.